Hi class, this lecture is about Excel Solver feature. It's an add-in that is available in Excel. It may not be enabled by default. It's a powerful tool used for solving and optimization, solving equations and for optimization. Um, let's start with making sure that the solver is enabled in your Excel. So let's open up an Excel file. In my case, it's already enabled. You can see it within the data ribbon inside the inside the analyze group, right below the data analysis feature. So the way to do that is go to File, go to Options, click on Add-ins, and then it should be inside the Analysis toolpack. Click Go. So it is enabled here, Solver add-in. If it's not enabled, click on it and click OK. That's how you have it over here. Okay. And once you have this, click on that feature. You'll see a window open up like this. So this has mainly four features. One is the setting objective. Um, so which target cell you want to set the objective function to. Okay, so if you're familiar with optimization, optimization involves an objective function which you're trying to optimize. Okay, then the type of objective you have, whether you're trying to maximize it, minimize it, or trying to equate it to a particular value. Sometimes you want that cell or equation in that cell to be equated to 0. Okay. One thing to be noted here is, let's say in this case, it's referencing cell T25. Okay. So that cell need to include a formula because it's trying to optimize variables in other cells that are referenced by that formula and trying to either find a maximum, minimum, or trying to match it to a certain value. Okay. So that's the objective function, and then what you're trying to do with the objective. Then the third thing is the variables. So you can select a bunch of variables, you can select multiple cells by pressing Control, or you could just drag continuously to get a range of cells like that, and then another cell if it's somewhere else. Okay, so it'll select it like that. So multiple cells in objective. Typically, you can only select one cell. It's recommended to only select one cell. You're trying to maximize the objective of one cell. Okay. Then the the fourth option is the third option is about adding the constraints. Okay, so let's say your variables can be varied from a certain point to a certain point, but what if your variables cannot go beyond a certain limit? Or the combination of variables, there's an equation between one or two variables that has to be satisfied. Okay, and that could be an equation, that could be a nonlinear, that could be an inequality or an equation. Okay, so it could be something like x1 plus x2 less than 4. Okay, if it has two variables, x1 and x2. It could be just that x1 is greater than 4 and x2 is greater than 5, or it could be a combination of them. Okay, so a lot of constraints could be added. Then the type of algorithms that's used to search for this optimization. Okay, there's the GRG nonlinear, the simplex LP linear programming, and then there's the evolutionary. Okay, so what are those? So the the three things I mentioned there, the primary one and the most commonly used one that I would recommend you use is the GRG, which is the generalized reduced gradient uh, nonlinear for smooth nonlinear problems. Okay, so it's like a gradient search optimization. So by the term gradient itself, you'll know that it's trying to differentiate. Okay, so it's trying to find a slope of the objective function. So that means the objective function should be differentiable. It should be a smooth function. It cannot be discrete variable. Okay, it cannot be just integers, or it cannot be just a count of numbers that cannot go to real numbers in between. Okay, so it should be a smooth function. The second one, the linear programming, simple linear programming, is when all your functions, the objective function and the constraint functions, are all linear equations or inequalities. Okay, so if you have a polynomial objective function of order greater than 1, a quadratic or a cubic polynomial, then you cannot use this. It'll give you an error right away. Okay. The third one is the is something that should work for everything. But a lot of time it will consume more time than the GRG function. If it's a smooth linear function, GRG will probably converge faster. Uh, the last one is mainly based on genetic algorithms, and it could solve complex optimization problems, including that are non-smooth, non-continuous, or involve discrete variables. Okay, so if your x values are all integers, for example, 1, 2, 3, 4, and they cannot take fractions, then you could use this as the solver. Okay, we'll try one example by using these three different ones and see the difference. Okay. So now let's look into some practical examples. First one is solving implicit equations using the Excel solver. So the optimization feature could be used to solve implicit equations. How? Um, Before that, let's just look into this particular implicit equation. Okay, this is an example from fluid mechanics. Um, and if you have taken a course in fluid mechanics, you are probably familiar with the Darcy-Weisbach equation. It's the fundamental equation used to estimate the head loss or the pressure loss, and very commonly used in pipe flows. Okay, so if there is a flow going through the pipe at a certain velocity, and you know the density of the fluid, and you know the length of the pipe and the diameter of the pipe, then the pressure drop from uh, within that length of L from the start to the end is basically F times L over D times half rho V square. Okay. Now what is this F? F is the friction factor. So the pressure loss is coming through some kind of loss due to friction. Okay. Now this friction is different for laminar flow versus turbulent flow. Even though this equation is universal for both laminar and turbulent, this friction factor is different for laminar and turbulent flows. So the pressure drop is different for either of them. For laminar, it's just a function of Reynolds number. The friction factor is 64 divided by Reynolds number. And again, Reynolds number is something I'm hoping you are familiar with. Okay, it's the ratio of inertial and viscous forces. So when it's in general Reynolds number less than 1000, 2000, it's laminar, and it's greater than 4000, it's turbulent. Now, if it is greater than 4000, one of the most commonly used friction vector equation is this, and it's called Colebrook-White equation. If you look at this equation, it's hard to find F implicitly, okay? There is 1 over square root of F here, and there is square root of F inside a logarithmic term here. So it's hard to find this function explicitly. So this is an implicit function. It's hard to find the value of F explicitly. So you have to iterate and then find the value, okay? There are several approximations for this Colebrook equation that are explicit function. One such example is the Swami-Jain equation, which I show here. In this case, F is only on the left side, and you can find out the value of F using this. What are the values inside this? You can see that there is an epsilon here. Epsilon is the surface roughness of the tube, of the pipe. I mentioned before the friction factor for laminar is 64 divided by Reynolds number. It does not care about the roughness of the pipe. So in laminar flow, The viscous forces are way higher than the friction or at the pipe. So the surface roughness is does not matter much. Okay, in turbulent flow, the eddies do interact with the eddies that are in the flow do interact with the roughness of the pipe. So it is important to use the roughness of the pipe in calculating the friction factor. So the variables that are used here, or the parameters that are used here, are roughness, diameter, Reynolds number, um, to find the Darcy friction factor, to use that in the Darcy-Weisbach equation. Okay, so without further ado, let's try to estimate this friction factor for a set of conditions, set of fixed conditions, and compare that with the Swami-Jain equation and see whether this equation is a good approximation of this equation. Okay. All right. So we have chosen some parameters. Density is 1000 for water, so we're assuming it's a water flow. Okay. So we have the viscosity of water, pipe roughness. We took a random pipe roughness for steel. And it's usually in microns, the roughness of a surface, it's in the micron scale. So that's why the small number. There's a pipe diameter here. So then we calculate Reynolds number using this equation. So we get this value, okay? And then we calculate the friction factor using the Swami-Jain equation, okay? So that is rather easy. With the Colebrook equation, we assume a friction factor, okay? Let's change that number to 0.04 for now, okay? And then when you assume that, you split this Colebrook equation into two sections, 1 over root f, which is the left-hand side, and then negative 2, and this log term with the square root of f on the inside as the other. So using this initial guess value, calculate 1 over square root of f. It gives you 5 on one side, and the right-hand side of that other equation gives you this. Now using Excel solver, you try to minimize this absolute error between the left-hand side and the right-hand side. When the error is almost zero, that means the left-hand side matches the right-hand side. So that gives us the right f value, okay? So our goal is to find the value of f here that makes this side and this side equal, which means this will be very close to zero. So how do we do that? Let's go to data analysis, data tab and solver. And our target cell is this, okay? And we want to change this cell, okay? And then we'll use GRG nonlinear and try to solve. Note that I haven't added any constraints. If I wanted to, I could add a constraint that the the Colebrook values should not be, because I already know it's close to 0.227. So it should only search from 0.01 to, let's say, 0.04. I could reduce the design space, but I'm not doing that because this should be a simple equation to solve. If it's a very complicated equation, it's best to constrain your variables so that it only searches within a smaller space. Otherwise, it is looking for a solution in a much larger space. Okay, so hit solve. So there's no error. So click OK here. So here the difference, the absolute difference is 10 to the power of -7, which is very close to zero. And you can see the RHS and LHS are almost the same value. Okay, and now the friction factor calculated by Colebrook-White equation is very close to this. The difference between Colebrook-White and Swami-Jain is roughly 1.026%. Okay, so we basically solved one particular Reynolds number. For one particular Reynolds number, we solved the friction factor and compared it to the Swami-Jain. What if we wanted to compare multiple ones? For example, if I had multiple velocities here, let's go to like 11 and let's drag all of these down. Okay, so in this scenario, how do we calculate all of these together? The the wrong way to do it would be to do, or the most difficult way to do it would be to solve every single row individually, okay? But the other option is to create a row that will, a particular cell that will sum the absolute error of all of these different rows. And then we could set this as our new objective and minimize this, okay? But one thing to note here is you want your initial guess to be really close to the actual number. So right now when I drag this down, it went all the way till 10. I shouldn't do that. I should probably drag it one more time alone without other things and drag it. So now the initial guess is not too far from the Swami Jain value. Okay. Let's adjust the solver parameters. Now let's say this is our new target or the objective to minimize. And then we are going to change all of these rows in that particular column, and then try to solve it. Okay. And one thing to note here is I'm not trying to set to the value of 0. I'm trying to minimize an absolute number. Okay. So in this case, it's an absolute number. Absolute number means it's always positive or 0. So when you try to minimize an absolute number, it's gonna, or summation of an absolute number, it's gonna try to get to the lowest number close to 0. I've seen that that gives less chances of error in the solver as opposed to directly setting it to a value of 0. Okay. Uh, you can try both ways and see how that works for you. Anyways, let's hit solve and see whether it's able to find a solution. Okay, it's saying it's finding a solution. It didn't give me an error. So let's look at the values. So why don't we plot this? Okay, so we have the Reynolds numbers and the Swami-Jain equation. So let's plot these guys first and select data and name it as Swami-Jain equation. Okay, and then gonna just copy and paste this one in there. And name that as the Colebrook-White equation. So they're not that far off, okay? And if you look at the errors, they're well below 1% for a range of Reynolds numbers starting from 60,000 to 66,000. So for this particular scenario, it seems like the Swami-Jain equation, which is this, is a decent approximation of the Colebrook-White equation. But either way, you're able to solve a range of cells and optimize it, and we're able to compare um, two different empirical equations for friction factor. Um, I'll just add the legend here. Okay, so that was the first example. Now let's try something else here. What if we change the solver type? Um, let's go to solver again. Data, solver. And I don't want to load the solver with a bunch of rows, so I'll go back to just one column here. Okay, sorry, and one row. And then I will say only the corresponding row has the variable. And instead of GRG nonlinear, I'll choose simplex linear programming. This should not work. You know why? Because our objective function, even though this cell, it's referencing two different cells which have nonlinear functions. Okay, so our objective function indirectly it is basically nonlinear. Even though in this cell it's just adding, sorry, subtracting two different values. That's a basic linear equation. It's referencing cells which have highly nonlinear equations inside them. So this should just not work. As expected, it's encountering an error in the objective cell or a constraining cell. The error, as we know, is that it's nonlinear objective function. Now, let's try, let's do one more thing here. Let's change this value to something else so that our solver can find the solution. So there's a 9% error. Let's change this to the evolutionary solver. Okay, let's go to solver, change this to evolutionary. One thing we have to do when you use evolutionary solver is to add bounds to the variable. So let's add some constraints to our variable. And in this case, our variable is this cell. And let's say it should be less than 0.04 add, and it should be greater than 0.015. Okay, so I added that, cancel. So we have evolutionary, we're trying to solve the absolute error in that cell, hit solve, and it should take a little bit of time. So as you can see, the GRG solution was much faster. This one is searching within our range of our the friction value that we just gave, the upper and lower bound. Of course, it's not going to try every single value within that. It's going to use an evolutionary algorithm such that it gets to a solution quicker. So when the function is smooth, it does not make sense to use this. GRG method is much faster. Okay, so it has found a solution. Let's see whether that matches. So yeah, it looks very close to the Somigene value, and it is very similar to the error that we had before, 1.026%. Okay, so it did find a solution. So now you know the difference between the three different solving strategies: the GRG, gradient optimization, the linear programming, and the third one is the evolutionary algorithm. Okay. All right. Let's look at another example. So in this case, let's go to a projectile motion example. Okay. So before we do that, let's try to understand the problem. So projectile motion is the motion of an object with an initial velocity, um, and there's no other forces acting on it other than gravity. Okay. So if you throw a stone, um, in reality, it will not follow the equations that I'm showing here because of the effect of drag due to the airflow, and if there is wind, things like that. Those are forces that are acting, aerodynamic drag that are acting. Sometimes there will be lift, aerodynamic lift that's acting there. Things like that are not included here. So the way that these particular equations are generated is when you send a stone or send a projectile at this velocity, the horizontal velocity is almost always constant. Okay, it's the same as how it is initial. There's no reduction in horizontal velocity. The vertical velocity changes due to gravity. Now let's look at how to solve this. So you have the initial velocity v naught, you have the launch angle theta, you have the gravitational force g, time t, any instant of time t, and then there is a total time of flight. Then there's a max height, which is h here, and then there is a total horizontal distance or range. Now, why is this an implicit function? This is an implicit function in theta. So suppose you want to find the max range. Um, what is the theta that is suitable for that max range? It is not easy to find that using this equation because theta is not an explicit function. Okay, so to find that, you can use the optimizer. Um, and let's say it has another constraint. So you want to find out what is the maximum distance possible when there is a constraint on the maximum height. So let's say the maximum height possible is x or h, but I cannot go to h. I can only go to zero point 0.9 times h. In that case, what is the maximum range possible and what is the theta needed for that particular trajectory? So for all this, it makes sense to use the Excel solver. Okay, so let's go into projectile motion Excel solver. So I have put in all the formulas here. We can check each formula. So the initial velocity, let's say that is a constant. Okay, it's launched at a certain velocity, 30 meter per second. You can change the angle, launch angle. That's the only variable you have. Okay, let's call this the variable. Okay, so find the optimum launch angle. Let's try to find the optimum launch angle for maximizing the distance. So let's keep this as the objective function for now and try to solve the angle. So this we are trying to maximize by changing this value, and we'll try to have no constraints for now. And GRG nonlinear, hit solve. That was quick. Let's look at the solution. The solution says 45 degrees. So this is actually well known in science that if you want to maximize your projectile distance, you have to aim at a 45-degree angle. It's actually well known. But let's make it interesting. Let's have a constraint on this height. Okay, so let's constrain the height to be less than 15 meters, okay, or 20 meters. If that's the case, what is the launch angle that'll give us the maximum range? So let's go to data, solver, add a constraint, which is basically this value is less than or equal to 20. Okay, add, cancel, solve. So now 41.32 is the angle and the range is 90.988. So range has decreased and the angle has decreased. Okay. So that's how we set this particular equation up. Let's look at one more example in optimization. So this would be fuel consumption optimization. Okay. So in this case, a car is traveling from location A to location B. It has a certain distance to travel and it has a certain amount of fuel in its tank. Imagine that you can only travel at one constant speed from A to B. You cannot change speeds in between, okay? And there's a maximum speed that is possible. There is a fuel consumption uh, versus car speed equation that is given here. Okay, it's based on some references in literature. Okay, so apparently it's a quadratic equation, and um, so we have to use this equation to figure out how the fuel is being consumed as the car is driving at a certain way. So if it's driving at 40 kilometers per hour, it's consuming close to 6.2 or something, 6.5 liters per every 100 kilometer. Okay, so it's giving you a fuel usage rate based on velocity. And it looks like initially it keeps decreasing and then it reaches an optimum and then it keeps increasing again. Okay, so what is our problem here? There are three things we have to find. First, find the speed that will save the most amount of fuel. Second, find the speed that will minimize the traveling time without running out of fuel. So in the first case, you save the most fuel. In the second case, you save almost no fuel so that you can maximize the speed or the traveling time, minimize the traveling time. In third case, you want to save exactly 1 liter of fuel. Let's see how to set up this problem in Solver and solve this problem. Okay, so fuel consumption. Okay, so we have this equation. Let's write down all the equations in here. The first thing is distance is 350 kilometers. Available fuel is 24. Those things are not changing. Max speed is 125. That's a constraint. So available fuel and max speed, well, they're both constraints. The variable is the speed, okay? And what we want to know is we want to reduce the fuel consumption, um, total fuel consumed, and sometimes we want to reduce the time. So let's look at the first one. Um, what will save the most amount of fuel? Total fuel consumed is basically fuel consumption rate times the distance. Okay, fuel consumption rate is liters per kilometer, and we just times the distance. So that's the total fuel consumed. And total time is basically distance divided by average speed. Okay, so start with, let's just put some random speed here. Okay, let's go to solver and in this particular case, we are trying to reduce the total fuel consumed by changing the average speed cell. And let's remove all the constraints. And then hit solve and find the optimum. So in this case, 19.168 is the minimum fuel that we have to consume, and the corresponding velocity is 65.94. If you look at it, that makes sense. That seems like the minimum point of this graph. So if you're arriving at the minimum point of this graph, you seem to be consuming less fuel. That makes sense. And how much will you save? You will save roughly close to 4.83 liters of fuel, which is nothing but 24 minus 19. Okay, so that's the amount of fuel you'll save. Let's look at minimizing the traveling time without running out of fuel. Okay, so we'll try to minimize this objective cell. Go to solver, and our objective cell is this. By changing the variable cell, again, the speed,
This time we'll add these two constraints, which are T12 is less than T4. What that means is total fuel consumed should be less than 24. Okay, that's a constraint. We cannot consume more fuel than we have. The other is the speed limit. So we cannot go above 125. Okay, so the speed 65, which is in column T8, location T8, should be less than T5. Okay, now let's solve this. Click OK and go back to our results. So the remaining fuel is almost zero. If that's the case, we can reach there in a total time of 3.76 hours. 3 hours and 3 and 3/4 hours, roughly, compared to the 5.3 hours before. And the max speed that we can travel at is 92.9. Okay, it's less than the 125. All right, so we found the second portion here. The third one is what is the velocity that will save exactly 1 liter of fuel? So the remaining fuel has to be exactly 1 liter. Let's go to the solver. Let's keep the same constraint and then say this, the target is 1, value of 1. Try solve, go back. Uh, I think we didn't change the objective cell, so we have to change the objective cell to this and try again. Okay, Alt tab. Yes, so the remaining fuel is 1 liter, and that means it has to run at a speed close to 90 kilometers. Okay, so now you get an idea of how to use the optimizer to obtain different objectives, change the constraints, etc. Um, I'll show you another example related to the assignment in the class. Um, so this lecture concludes here. Thank you.